Hello, my name is Daniel, and this is my video interview for CS61B. And sorry about the poor camera quality. I'm currently at home and don't have a better way of recording. So today I'll be talking about minimum spanning trees and some of their properties, and then I'll talk about one of the canonical algorithms on how to find minimum spanning trees called Prim's algorithm. So first, let's talk about the conditions that you need for it to be a minimum spanning tree. So there's three parts of it. It's minimum, it's spanning, and it is a tree. So first, the properties of a tree are, as we might have went over earlier in the class, is that it's connected and that it is acyclic. So for it to be connected, we say if there's multiple components in there, they all have to be able to reach each other from a path. So this is currently not connected, but once we draw it like this, it is connected. And for it to be acyclic, there can only be one path to each one. So currently it is acyclic, but if we draw this, we can now go multiple different ways and loop around to get there as well. So it is cyclic in this case. So this would not be a minimum spanning tree. Another thing is that it's minimum. So the condition for minimum is that we say there are minimal edge weights. And so in this case, going back to this one again, if we had something, or if the original one was like this and the edge weights were 1, 2, and 3, then for it to be a spanning tree, or a minimum spanning tree, then the edge weights would have to be absolutely minimal. So in this case, this would be our minimum spanning tree because the sum of the edge weights is the smallest in this case. So now talk about some of the properties of a minimum spanning tree. A useful property that we talk about for how to find minimum spanning trees is called the cut property. And the cut property says that for any cut, which is just a partition of nodes into two non-empty sets, so if we had a graph that looked like this, and I'm just going to draw this graph real quick. So a cut would be any partition of the nodes into two non-empty sets. So if I just partition it this way, this is one possible cut. Another possible cut could be something like this, where I just split the nodes into one set and the last one into another. So the cut property says that the minimum edge across any cut is part of the minimum spanning tree. So in this case, if we had all our edges like this node was connected to every other node, then the minimum edge across this cut would be part of our minimum spanning tree by the cut property. So if we had 1, 2, 3, 4, and 5 as our edge weights, we can guarantee that this 1 is part of our minimum spanning tree. And I won't go over the proof now because just for time's sake, but that is one of the properties we assume for a minimum spanning tree. And going off of this, we can kind of reason through how this property can be used to find minimum spanning trees. So I'll just go over an example now called Prim's algorithm that uses this property. Or first I'll talk about Prim's algorithm. And Prim's algorithm says that because of the cut property, we can essentially add edges based on the cut property. And starting with a single node, we'll continually add edges and change our cuts and add edges in this way because we know the edges we add will be part of our minimum spanning tree. So here's an example graph now. And using this graph, we'll try to create the minimum spanning tree using Prim's algorithm. And we can arbitrarily start at any node because we know all of them have to be included in our minimum spanning tree. But for this case, we'll start with A. And also another caveat is that we'll assume that the edge weights are unique here, because if the edge weights are non-unique, then the minimum spanning tree is not exactly unique. But for this one, all of our, or not all our edge weights are unique, but we'll find that we have a unique spanning tree anyway. So going off of this, we'll start at node A. And following Prim's algorithm, we say that we want to add the minimum edge not in our tree into our, the minimum cut, the minimum edge across our cut into our spanning tree and make this part of our spanning tree. Sorry. So we have D, C, and B here. And we see that the minimum edge across this cut from A to any other part of it right now that it can reach is our 4, so we can add 4 to it. Now we have two more, from B we have one more possible edge we can add, which is E now. And from this cut currently, we see that our minimum edge to add is 1, so we'll add that. And this adds the possibility of adding our F edge as well now. And we see our next possible minimum cut, or minimum edge across a cut, which is ABC to the rest of the graph, is now 2, so now we add 2. Continuing on, looking for the minimum one, now we have 4 as the minimum, so we add 4. And now F is part of our cut, so now we have E and G left. And from this whole cut here of our connected graph to the rest of the graph, the minimum edge is now 1, so we add this one. And then now there's only one node not in our cut, and the minimum edge to that cut is 6. And so this is our minimum spanning tree now. So we can see how Prim's algorithm helps us find minimum spanning tree using the cut property. And just going over the runtime of Prim's algorithm real quick, if we kind of remember back to Dijkstra's from a couple weeks ago, we can see how it's kind of similar in that we keep looking for the minimum as we go. And so essentially this is the same as Dijkstra's, and we can implement it basically the same way using a priority queue, which will speed up our implementation a little bit. So just talking about the runtime of this, using a priority queue, we can see how we'd like to have 3 operations as part of our algorithm. We'll have insertion, deletion to pop off our minimum edges, and then decrease priority so that we can change our priorities once we remove remove a node from our cuts. So to insert, assuming we're using a priority queue, our insertions will take log v time individually since we have v nodes in our graph, and we'll have v possible insertions since we have to insert all of them in there. To delete, we pop off the minimum edge, which is the one we want to add to our minimum spanning tree, and then we have to resort our heap, which also takes log v time individually. So this is the same. And for decreasing priority, we have e possible edges in our graph, so we'll have to decrease the priority possibly e times when we are, or some multiple of e times when we're trying to sort our edges to see which one we want to add. And each one, or the heap, is still bounded by v vertices, and each sort would take log time, so we still have e log v. And since these are all separate, we're really adding these all up for our runtime, and so this is going to be bounded by e log v, so that's the runtime of Prim's algorithm, e log, big O of e log v. So that was a rundown of Prim's algorithm and